Let's start by looking at what happens in a single-threaded process. The process is described with all of the process-related state that includes the address space, so the virtual to physical address mappings, its stack, its register, since it has a single thread. Whenever this process makes a system call, it traps into the kernel, executes in the context of a kernel thread. All of the information about the state of this process, we said, is contained in its process control block. And let's for now assume that we're dealing with just one CPU. Let's now make the process multi-threaded. So this will look like our many-to-one model, where many user-level threads are supported by one kernel-level thread, and that there is a user-level threading library that manages these threads. This user-level library will need some way to represent threads so that it can track their resource use and make decisions regarding scheduling and synchronization. So it will have some user-level thread data structure. If we want there to be multiple kernel-level threads associated with this process, we see that currently we have the process control block containing all the virtual address mappings as well as the execution state of the process thread. We don't want to have to replicate this entire data structure with all this information just so as to represent different stack and register values for the kernel-level entities. So we will start splitting up this process control block structure to separate the information that's specifically useful to represent the execution state of the kernel-level thread, so their stack and register pointer. And this will still have, the process control block will still have the virtual address mappings, as well as some additional information that's relevant for the entire process, so for all of the kernel-level threads. Note that from the perspective of the user-level threading library, the underlying kernel-level threads look sort of like virtual CPUs. So the threading library looks at the user-level threads and decide which one of the user-level threads will be scheduled onto the underlying kernel-level threads. Unix-based systems, for instance, have certain operations called set jump and long jump, which are useful when we need to save and restore the context of a user-level thread.